I trained a neural network to effectively pilot a fully autonomous Kamikaze drone within a virtual reality simulation, and I will detail exactly how I managed to create this. War has changed. New developments in energy density technologies have allowed for the creation of small FPV drones. The use of these drones has been most noted in Ukraine, but they are now being used all over the world. The threat that these technologies pose has created countermeasures, and then countermeasures for those countermeasures. Look to the west, and you see companies like Anduril or Palantir developing these advanced anti-drone technologies, whether they jam or fry. And in the east, you see Russia and her fiber-optic connected drones, and the web that these drones have spun over Ukrainian cities. It's quite the sight to behold. I believe the holy grail of drone technology is full autonomy. You don't need a pilot, you don't need to worry about jamming, because it's like a little creature in the air, just as if you were to attach something to a bird and let it fly into enemy lines. You can't jam a pigeon. Autonomy advancements could also lead to the development of terrifying drone swarms. Clusters of drones attached to small plastic explosives could sweep over a battlefield or a town and totally eliminate defensive positions. I think the idea of this technology is incredibly interesting, which is why I wanted to tackle it in this project. And I think watching this video will give you a good insight into what it will actually look like, both autonomy and swarms. I'd like to briefly say that this project is actually a side project to a larger goal of mine. I am primarily a virtual reality developer. That's what I've spent most of my time on. One of the largest problems for VR and physics-based VR is truly interactable NPCs.
Hello there. It's good to see a friendly face.
If you have, say, an RPG game in a flat-screen game, you will use your mouse and your keyboard, and the domains of interaction are very limited. But in VR, you're literally able to touch the NPCs. For now, when you do directly interact with an NPC, they look really stupid. And this is a massive problem because how do you have the NPC respond? You have to have NPCs so dynamic, so interactable, that they can respond exactly how a human would. Because that's what you're simulating. You have to fully simulate a human. And it's a shame that's so difficult to do, because if you look at the most impressive and interesting parts of video games, you look to the NPCs, the most dynamic creatures in any scene. I believe neural networks are the path to that full NPC interactability, and this drone project using the neural network is a stepping stone to a full biped, and all of the interactions a full biped can do. That's walking, jumping, running, and interacting with their hands and arms with objects around them. I think that's an exciting prospect that I will explore in the future, but this is a stepping stone towards that future. So about neural networks for the uninitiated. What are they? How do we use them? How do we train them? Some time ago, I was asking myself these very questions, and I decided the best way to answer them was by getting my hands dirty, learn by doing, and make them from scratch myself. When most people make AI models, they're relying on pre-existing libraries, code that they did not write themselves, and maybe they use a very high-level language like Python in order to bring all these components together. So to garner an intuitive understanding, I first wrote a neural network in C#. Neural networks are deceptively simple data structures. They're pretty much a graph composed of nodes that contain a bias, connected by multiplicative weights such that if you are to take a forward pass, we call it, for every layer of nodes, you are transforming the information with both a multiple and a bias, an addition or a subtraction. The real hard part with neural networks is how we make them effective in a real-world job. That means transforming each of these weights and biases such that the inputs get transformed into useful outputs. The simplest way to achieve this goal is something called a genetic algorithm. They work in short by knocking these values, these weights and biases around randomly, and testing whether or not they're good or bad, if they produce good or bad outputs. We call it a genetic algorithm because several agents will be doing this simultaneously. You might take the same base neural network, perhaps it's a sample of the past few most successful neural networks, and you test them against each other in the very same environment. The ones that are most successful live on. They reproduce, let's say. And those that don't, well, they get cut. Thus the genetic analogy. It's evolutionary. Now, I knew that this algorithm wasn't very powerful, so I chose an extremely limited action space. One of the greatest mistakes that I see engineers make when first learning how to use these tools, these ideas, is they take off too much of a bite. They try to do something very hard, very complex, at first, a very large neural network, and they end up failing, which is quite demotivating. You have to start with principles, with basics. I chose a drone, the object of interest which I'm attempting to automate, and chose to squish this three-dimensional machine that can fly around in space into merely one dimension, with one output, that is thrust. So I locked the drone's movement on one axis, gave it one button, and if it pushes it, it goes up, and if it doesn't push it, it goes down. It's a task so simple that children and even animals can do it on a very short order of time, and ordinarily, if you were an engineer, you'd use something called a PID instead. So invariably, when I started the simulation, the drones effectively reached their target within a few dozen generations. The genetic algorithm worked. Unfortunately, I found when I tried to apply this same algorithm to a more complex action space, to two-dimensional or three-dimensional movement, just like a real drone would do, it was suddenly quite unsuccessful. And ultimately I learned quite a bit, but I moved on to bigger, better, more powerful algorithms. Machine learning has come a long way since genetic algorithms. One of the most common and most powerful approaches to training our neural networks is called PPO. Proximal Policy Optimization. Now, that name sounds absolutely meaningless, so I'm going to break it down into its elementary parts. PPO falls under the category of deep reinforcement learning. What that actually means is it uses something called backpropagation to adjust the weights and biases of the neural network in an intentional direction, not randomly like the genetic algorithm, but instead based off of what kind of input we want and what kind of input we have, the delta between those two. The math that underlies how each of these nodes are changed is called backpropagation calculus. In order to implement this backpropagation calculus, we start at the end of the neural network where the outputs are, and we iteratively look back at each of the layers using backpropagation calculus to carefully adjust the weights and biases such that given the input it was given, we can change the output to be the output that we desire. In supervised reinforcement learning, we can pretty much just use that algorithm in order to get the kind of neural network we want, because in reinforcement learning we have labeled data which will tell us exactly how bad each of our outputs are. But we're doing something a bit harder called unsupervised reinforcement learning. This is where the more unique components of PPO come in, because we need some way of identifying if the actions we take are good or bad. That may seem obvious. You want the drone to go to the target, not go away from the target. But you might imagine some action, like, say, gaining altitude, that is bad because it takes you away from the target, but is good in the long term because gaining altitude will enable the drone to reach its desired location much faster. In order to properly implement backpropagation, we also have to know exactly how good or bad each action is, which effectively means we have to approximate the correct thrust for every propeller as it tries to reach its goal. This is obviously quite the conundrum. PPO solves it by using two twin neural networks. One of them is called the policy network, which outputs the action that the drone takes. The other one is the value network. It estimates the value, how good or bad each of the actions the drone took into the future. This is how we get around the pitfalls of a neural network that is trained by only taking the derivative of the distance to the goal, which allows us to evaluate decisions on the long term, so that we're not looking at short-sighted optimization of distance. This explanation is very high level and isn't necessarily specific to PPO, but methods like PPO. But that's pretty much all I'm willing to explain to you, my YouTube audience. I wanted the training of this drone to be as realistic as possible. In order to achieve that, instead of having something like one thrust at the bottom of the drone and a direction it can move in, I had all of the 4 propellers properly simulated as they would work in real life. There's absolutely no trickery going on, there is no animation, there is only physics. So in order to go forward, the back propellers have to increase in speed and the front have to decrease. It has to lean forwards such that the vector force of the total drone is going forwards. This is achieved by putting an actual rigid body force at the 4 corners of the drone where the propellers are. Even the yawing of the drone, that is, its turning left and right, is achieved by calculating the yaw as it would be in real life based on the speed of the propellers, that is, the torque and the anti-torque. Naturally, such a realistic configuration is difficult to control for any human being. certainly not directly. And I figured much of that would be true for a neural network as well. You want to make the action space as simple as possible, as easy as possible for your neural network. I had learned as such with my experiments with genetic algorithms. When I tried to brute force 3D movement with just the pure physics, I failed. If I can't pilot the drone, why should the neural network be able to? To develop a solution to this problem, I looked back at one of my most favorite games, Scrap Mechanic. It's a physics engineering sandbox, and some time ago I was obsessed with the idea of making an easily controllable flying vehicle, an aerial vehicle. What you see before you is a product of that experimentation. It kind of looks like a UFO. And what's important about this UFO is it has the exact scheme necessary to control a drone. It has pitch, which is the anterior and posterior tilting of the vehicle. It has yaw, which is the left and right rotation of the vehicle. It has roll, which is the left and right tilting of the vehicle. And it has thrust, which is how much it goes up. And to make all of these actions easier for the neural network to understand, I had them as set values as opposed to directions of movement. That means the neural network can set a pitch of 45 degrees, and it pitches to 45 degrees. There's no set amount of time it has to rotate forwards. That's handled by the PID. Now, given this control scheme and the PID, I was able to pilot the drone myself. Now that I could do it, I knew I had to force my neural network to train on it. Training requires an environment, and my first one was a black box. The rewards are pretty simple. If the drone crashes into the walls of this chamber, it loses its points, and if it remains near to the target, it gains points. After some amount of training, I produced this result. Clearly, it's effective at reaching the target, but it's only effective at reaching the target. That erratic spinning behavior is quite undesirable. I think what happened here is the drone found that the easiest way to remain close and stable to the target was to spin, because spinning is actually pretty stable. Many older rockets and even modern missiles spun for the sake of gyroscopic stability. It takes a much greater amount of energy to move a spinning object off of its spinning axis than it does a non-spinning object. But more importantly, for the sake of a simplified control system, pitch and yaw commands can be timed to fire once per revolution when you achieve the desired angle. So maybe you only have one RCS thruster instead of 4. Taking it back to the drone, it probably figured out it only needed to rotate in the direction of the target every 360 degrees. Perhaps it only figured out how to tilt forwards, so was doing that every revolution. It was also slower and more stable, so it might have been able to stay near to the object longer and not crash into walls. So I knew I had to take a different approach. The walls of the chamber over-rewarded stability, so I removed them. The target was too close to necessitate speed, so I moved them farther away. And I added a large reward for the drone actually looking at the target that it's supposed to be flying towards, so I wouldn't have this erratic spinning behavior or anomalous behavior like the drone flying its butt towards the target, because obviously we don't want that. Initially, the training was pretty slow because it's hard to figure out if a drone is failing unless you have walls that it's crashing into, since once it crashed, the simulation ended with a large deduction in its score. These drones instead wasted time flying off into the void. I was afraid that I'd made a horrible mistake in removing the previous environment and that I would be left with a similar result that I had at the end of my genetic algorithm testing. But lo and behold, when I tweaked some hyperparameters and the way the rewards are dished out, I found an absolutely excellent result. Not only were my drones looking at their target, they were actually quite fast at getting there. I could place a target hundreds of meters away, tweak its thrust, and so long as this drone could beat the force of gravity, it would get to the target as fast as possible. This behavior, this ramming behavior, was exactly what I was looking for, and it's exactly what's necessary for a Kamikaze drone. I even found that if I placed these drones in a group and had them have the same target, they could act as a swarm. What I really like about this is just how organic they look. They kind of look like they're a machine-animal hybrid. Now the problem with that is they're about as foolish as an animal, maybe even more so. Once I placed a target on the opposite side of a wall from the drone, it was no longer quite as effective, and that certainly won't do. So now we can get places, but if there's anything in our drone's way, it gets stuck. If I were making this neural network for the real world, what I'd do is set up some sort of vision algorithm that could identify that there's a wall there that's blocking our path. Said algorithm would use its wisdom to place the target, say, above the wall, and the drone would fly above the wall and then be able to see the point of interest that's across the barrier, say a vehicle. Then it has a straight line to fly towards it. Beyond the obvious ethical questions of making the drone fully capable of operating in the real world, vision-based guidance based off of neural networks, requires an order of magnitude more input. You have to take the entire screen. That means a lot more training compute I don't necessarily have. Thankfully, in this physics simulation, we're completely omniscient, so I don't need a neural network to extract that information from what it sees. I can just take that data directly from the physics simulation. But that takes us back to the original problem. How do we generate these waypoints that can get us over walls, as I described before? To illustrate my solution to this problem, I want you to imagine the drone as kind of like a rodent in a maze, and these waypoints as pieces of cheese. If we want the rodent to most efficiently navigate the maze without bumping into walls, we have to figure out the most efficient path to our point of interest. In order to generate such a path, I used something called A*. It's kind of like Dijkstra's algorithm, it's pathfinding. Except instead of searching through the whole maze and trying to find the most optimal path, it uses a number of heuristics to make the compute less hard on the computer. Faster, in other words. But to do that, we must first turn our complicated world, which may be filled with buildings and trees and their associated branches, into a navigable graph. I generated such a graph by first defining an area around the drone and the point of interest. It's just a big box. I then split this box into 8 smaller boxes in a sort of octree. I did this iteratively until I found a desirable depth that accommodated the flight of the drone. If the boxes are too large, they're not able to navigate smaller spaces, and if they are too small, they're not really great for a drone and they're hard to compute. A drone needs some amount of distance between the waypoints so that it operates at a high speed. Once I have all of my smaller boxes, I can then do a boundary box check between the bounds of the box and the smaller colliders that are within the scene. This tells me which of the boxes are most obstructed, most occluded by colliders. These are the boxes I will obviously ignore. For the boxes that are partially obstructed, I assign a penalty for traversing through them for the algorithm. This combination of A* pathfinding with extra heuristics and a voxel volume generated by an octree is something I call Voxilar. It's how the drones generate these waypoints, these pieces of cheese, to follow and eventually reach the point of interest, making them much more interesting and effective combatants. If you remember, I'm a virtual reality developer. I don't just want you to look at these drones and say, ooh, they're pretty. I want you to be able to interact with them combatively. And what better way to do that but with the firearms that are used in conflicts across the globe? And yes, that means there's a demo of this project in the description. You can fight these drones today. I implemented specific features for weapon handling into my physics backend. I also modeled 2 firearms. One was a shotgun, the other was a 1911 pistol. When I implemented both of these models in game, I found an interesting difference between their behavior. In virtual reality, it was much easier to handle the one-handed weapon as opposed to the two-handed weapon. It turns out there's actually quite a bit of math that goes on to virtual reality weapon handling, and I didn't have time to implement that. So although the shotgun looks cool, it's not in the released demo. On the other hand, the pistol is, and it's fun to use. All of its interactions are physics-based, meaning you have to physically pull back the rack, it produces a force upon impact with an object, it even produces recoil directly into your physics-based body, meaning if you shoot this firearm in the middle of a small pond, it will propel your body backwards. And the cartridges it expels are fully physics-based. But most importantly, it's real good at blowing up drones. Now that our AI is ready, I think you'll agree with me that that old coat of paint, that old drone model is not doing it. It's not screaming kamikaze. So I swapped it out for one I think is far superior. Not only does it look better, it also functions better. Each of the propellers is fully animated, rising in speed as the drone increases in thrust, and they do so differentially, meaning just by looking at the propellers you can kind of tell what the drone is thinking and doing. I think it's super cool. And of course it has audio to go along with it, higher pitched and louder as the thrust increases. So I hope for this to spread terror on the virtual battlefield. Speaking of which, I think that needs a new coat of paint as well. What you see in this scene is just a blob of dev textures and geometry. To fix that, I modeled a chamber to act as a real-world analog. You can touch the grass, feel the sun, and even climb the trees. Of course, the water is also fully physics-based as well. You can swim in it. But what's most important is this button. It spawns the drones. Many, if you are so daring.
That could be a problem because a lot of drones are tough to deal with. Turns out, this game is actually pretty performant with all the neural networks running. So I can shoot my watermelons. Let them interact with the water physics. I'm going to try to see if I can evade the drone. So I might go and find myself some shelter, say this fine establishment right here. But it's still going to come for me, even if I try to go around the pillar. I'm about to get screwed. One thing that is nice about this is you can actually climb the trees. As you can see with my advanced physics simulation, I can jump up and grab them. Now you're actually fairly weak, so you have to use your momentum, otherwise you'll really go slowly. But given you're clever enough and acrobatic enough, you can totally get on this roof using that tree. It's kind of hard to stay on the roof, it's slippery. Now, one limitation of this simulation is this house right here. I'm going to spawn a few more drones. If I go inside of it, drones have a little bit of difficulty actually tracking me, because I didn't write an algorithm that can really tell the difference between like the space and the mesh collider of this house, so it kind of just thinks it's inside of a wall. But so long as it has line of sight to see me, it is pretty effective. Now I want to see what it's like when I spawn a whole lot of drones, really show off that swarm capability. So I'm just gonna... Uh-oh. Oh no. Oh no. Oh. One problem they do face is if you group up a lot of them, they can get flipped over because they get blown up. As soon as there's another explosion, half of them get flipped back over. I'm trying to pick up a pistol. There we go. Really try to time myself accurately. There we go. Oh boy. This scene is fully ray traced by baked light maps. This means it should look fairly pretty on your end. Looks like one even got blown inside this house, or maybe it's already here. My. I can hear the faint humming of more, but oh. I think that's about it.
As I said, the next step is bipedalism. I'm gonna post a video documenting that in the future, so if you're interested in that or advanced virtual reality, check out the rest of my channel. Bye-bye!